evidence for some specialized reflectance in a part of the light field that we humans live in, and that's polarized light. And I'm assuming that everyone in this session is familiar with the sensory drive, sensory exploitation model that John Endler and Mike Ryan made famous a couple decades ago. And recently, Mike Ryan and I reviewed the evidence for this model, empirical evidence for the last 25 years. I just want to remind people that at the basis of this model for trait diversification are differences in environment and unique attributes of species environments which shape the sensory systems, which then place constraints on trait evolution. And since I'm going to be talking to you today about polarized signaling, I'd like to first give a bit of a definition to it, for it, as well as tell you where we expect to see it. So polarization refers to the vibrational plane of the light field. Remember that photons have both a wave and a particle nature to them. And so polarized light refers to the vibrational plane and the direction of that vibrational plane, and when those photons are traveling in phase with each other. Now, there are certain compounds or molecules on this planet that are really good at polarizing light, and one of those is water. And so we are aware of this feature of water whenever we go out on our boat and have to put on our polarized sunglasses to block out a specific direction of polarized light that we call glare. So not surprisingly, there are two main ecosystems on our planet where we tend to find a high degree of polarized light: the sky and aquatic environments, so where there are water molecules. Also not surprisingly, organisms that inhabit these ecosystems have evolved sensitivity to polarized light. And today I'm going to be talking to you about fish, and 6 different families of fish have shown evidence for sensitivity to polarized light. So I'm going to start this talk by first examining natural selection and how it shapes polarized reflectance, allowing some open ocean fish to improve their camouflage out in the open ocean. So this was work funded by the Navy, and they want to know how they can better hide things in the open ocean, as you can imagine. They've been interested in this for years, and for several decades now, the common conventional strategy for hiding things in the open ocean is to cover your body or your submarine with mirrors. And this concept was put forth by Sir Benton in the 1970s. And it works really well for many parts of the ocean where the light field is homogeneous or symmetrical on your left and your right side. But there are parts of the ocean where it doesn't work very well, and those parts are very near the surface or the epipelagic zone. And that's because the polarized light field predominates there. And the polarized light field is very subject or changes with the changing in position of the sun. So the main plane of the polarized light, or the vibrational plane, is always orthogonal to the incoming rays. And so as the sun tilts across the sky, the main plane tilts with it. And as you can see, this sets up a really heterogeneous optical backdrop for fish, especially when the sun is anywhere but overhead. And so an animal who's going to try to use the vertical mirror strategy to blend in these highly complex light fields, as is simulated here, is not going to do a very good job because it will be reflecting portions of the polarized light field that don't match its background. So being charged by the Navy to go find a solution for this, or look to nature for a solution, we first built a video polarimeter, and that we would really be Dr. Parrish Brady, who's a biophysicist. And then our collaborators built an automated rotating platform to allow us to measure that continuous variation in an azimuthal plane. And then we measured live fish and optical backdrops in really fun places around the world, such as the Florida Keys and Curacao. And this was a large operation. That'll wake you up. A large operation with a lot of different kinds of scientists involving physicists and electrical engineers and biologists. And so we would go collect live fish early in the morning, bring them out on these boats, restrain them with a mesh against a mirror, as well as diffuse reflecting surface, and then set up the video polarimeter in different positions, and that way we could measure both the backdrop, the mirror, and the fish simultaneously spun it around an azimuthal 360 spin in different configurations with the sun in different positions in the sky. Now I'm sure you're much more interested in seeing what it looks like from the camera itself. And here's an azimuthal spin of the video polarimeter measuring the fish as it spins around. And you can see, I'll just use this, here's the fish, it's a big-eyed scad, here's the mirror, here's the background, here's a diffuse mirror reflector. You can see at some angles, the fish is doing better than the mirror in terms of matching the background light, and in other angles, it's the other way around. Oh, and that's me swimming time, highly polarized person. So we did this for a number of weeks in a number of different locations and collected a couple thousand measurements from all different angular parameters. And so there's a number of ways you can analyze this. So to start off with, we simply took all the measurements we collected and asked a simple question. Does the mirror, does a diffuse reflecting mirror, or the fish do better at minimizing contrast in this highly complex light field? And for contrast, we used a Stokes contrast measure, which is a composite of both intensity and polarization elements Q and U. And as you can see here, in the simple averaging approach, the fish, in this case the big-eyed scad or look-downs, which are open ocean carangid species, are significantly lower in contrast than the mirror surfaces. Now we were curious whether or not this was a simple product of all fish skin, or was this something that was unique to the open ocean environment. So we took these measurements with other fish species, including some reef-dwelling carangids, and we don't see that pattern. So it's suggestive that it is something unique about the open ocean environment that is acting or applying pressure to modify fish reflectance. So being evolutionary biologists, we were much more interested in examining ecologically relevant viewing angles. So we restricted the analysis to predatory pursuit angles or chase angles, which we define as 90-degree cone of the tail end of the fish as well as the head. And when we do that analysis, we find a more significant drop in contrast with fish species relative to the mirror. And again, once again, looking at non-open ocean fish, we don't see that pattern of reduced contrast. We've also done this looking at specific angles. So we had the fish in different positions relative to the camera. And for each of these plots or data points, that represents which surface, a fish, a mirror, or diffuse mirror reflector, offers the best camouflage at that particular viewing angle. And you can see that at these chase angles, the fish is predominantly the best camouflaging surface. So we've also started to analyze it from the individual perspective. And so we used 11 fish to do these measurements in the field. When you simply take all those measurements, collapse them down to an average, and compare that to the mirror's average across all those conditions, once again, we do see a significant improvement in Crypsis by these fish. And even to bring home the point even further, we reduced our analysis to the 5 fish with the most robust set of measurements. And you can see that we obtain the same pattern. Like here's the fish averages, here are the mirror averages, this is for the full Stokes, and then each of the components of the Stokes contrast measure, intensity, Q, and U. So hopefully this is a convincing set of data suggesting that natural selection has shaped the reflectance properties of these fish in this very complicated light field to improve their Crypsis. So now I'm going to switch to sexual selection and investigate whether or not sexual selection also has the power to modify polarized reflectances in aquatic systems. And for this, I'm going to be telling you some research from a freshwater system using the northern one of the northern swordtail Xiphophorus nigrensis. I'm a big fan of this fish. We've been working on it for a while. And we know from lots of studies that these drab females, pay attention to the ornaments of males. And so we were curious, and it was just too darn tempting to be in a lab with a bunch of swordtails and a video polarimeter, not to start taking videos of these guys. So what you're looking at here is a video clip of 3 male swordtails being illuminated with horizontal polarized light. That's the colors here are coded for different angles of polarized light. And what you can see is these males, as they turn their bodies, are actually reflecting different angles of polarized light. as in terms of signal evolution, this would be a great signal strategy to contrast with the background. So to ask whether or not there was any signatures of sexual selection going on, we first examined whether or not there was sexual dimorphism in these features. And so this is a figure of a male swordtail, color-coded by the degree of linear polarization. And we examined males and females in 8 different body regions. And anytime you see an arrow, represents a body region where we found the signs for sexual dimorphism, with males providing larger polarization contrast to background than females. So the next thing that Gina Calabrese, a master student in the lab at the time, did was really try to understand if females were paying attention to this polarization augmentation. So she built a highly specialized matrix chamber that could vary the polarization features of males without changing brightness or color of the males. And how we did this is by special placement of polarizing filters with respect to diffusion tanks. So on this side of the tank, we have the same amount of light going in, first becoming depolarized, then becoming highly polarized and illuminating this male. Meanwhile, on the other side of the tank, we have the light first being polarized and then becoming depolarized. So it's the same intensity, same color. The only difference between the size of the tanks are the polarization component. And she measured the amount of time females spent with each of these males, as well as in those different kinds of polarized environments as controls. And what she found is that females do attend to the polarization ornaments of these males, with spending much more time in front of males who have their polarized ornaments in full show relative to the depolarized males. And meanwhile, in the controls, they showed no preference for these types of different light environments. More excitingly, she actually found evidence for dynamic signaling in this particular trait. So what she set out to do is she had males and females in different tank environments where she would measure their polarized reflectance. And she did this in both social conditions with conspecifics and then asocial conditions alone. And what she found is that in males, which are the data in blue, but not females in green, that males were modulating their signals such that in social conditions they increased their contrast, both within body contrast and body to background contrast, relative to asocial conditions. And this is a highly conservative measure because we took all of our measurements from video frames where males and females were in the exact same position orthogonal to the camera. So what this means is that this wasn't even taking into account all that movement and angular variation that males display during their courtship display. So most likely this is an underestimate of how much males can increase their contrast using the polarization signaling. So hopefully in this short time I've convinced you that in highly polarized environments we should expect both natural and sexual selection to be shaping the polarized reflectances of organisms that live in these environments to either help them camouflage or communicate better with others.